Hi everyone, welcome back. So today we're on the fourth video of the series, and we are going to discuss. So let's start EM04. So today we're going to discuss EM tools. So we'll develop basically a couple of tools that we'll use to solve problems later on, um, to solve Maxwell's equations in different problems. Okay, so let's get started. First thing we're going to look at is equivalent magnetic currents and charges. Okay, so what's the big idea here? The idea is that we have Maxwell's equations and we want to make them symmetric. We'll see what that symmetry means, so that that symmetry in the Maxwell's equations will give us a nice tool called duality. Right, so in order to do that, we first need to develop an equivalent magnetic current and charge. And we know that in Maxwell's equations, we have electric currents and charges. And we know in reality, there are no magnetic currents and charges, but we want to make like a fictitious or a mathematically equivalent magnetic current and charge. Okay, that's the idea. So how do we do that? So we can start with Faraday's law, Et, and I can expand this out. So this is nothing but minus mu naught plus chi m dH over dt, and this is in an isotropic medium. So, sorry, isotropic and homogeneous medium. I can pull that mu out, right? So that's nothing but minus mu naught dH over dt minus mu naught dm over dt, right? Where m is nothing but the magnetization vector. And now I can call this as a magnetic current. So this is the definition of the magnetic current in some sense. So I can define an equivalent magnetic current to be nothing but mu naught dm over dt. Right, so with this definition, if I rewrite Faraday's law now, it's curl of E equal to minus dB minus mu naught dH over dt minus J M. Right, so this looks very similar to modified Ampere's law, right? Where you had curl of H equal to epsilon naught dE over dt plus J. And we'll kind of review that at the end, but so we can do something similar to Gauss's law for magnetism. Right, so I can write this as curl of mu naught times H plus M, which is 0. Right, so I can rewrite this as mu naught times curl of H equal to minus mu naught times curl of M. And this I can write as rho M. It's an equivalent magnetic charge. Right, so that gives me like nothing but curl of H equal to rho M over mu naught. Right, so in summary, you can say that you have Jm, which is mu naught dm over dt, and rho m, which is minus mu naught times the curl of m, divergence of m. Let me put this in a nice box. See if it makes a nice box for us. Okay. It's important to keep in mind that these are not actual sources. Actual magnetic sources. Instead, what we are doing is we have a material with some mu. We are replacing mu with mu naught, which is free space, plus these magnetic currents and charges. That's the idea. So you can think of it as if that these currents and charges represent small, tiny magnetic dipoles that are in some medium, right? So the medium essentially is representing or has these atoms that have, small magnetic dipoles. I can say instead of placing the medium, it's really the dipoles that capture um, how the medium responds to an incident electric and magnetic field, right? So instead of dealing with the medium, I can get rid of the medium and just deal with the charges and the currents, the equivalent charges and currents, and that's the idea. Okay, so in this case, we replace mu with mu naught, and then we place some charges and currents, but there's nothing special about mu naught. You can use any other mu as well. So we can look at that next. So we start with curl of E is minus dB over dt, which is nothing but minus d mu h over dt. And I can add and subtract another mu, arbitrary mu. And I can call this term as the mu jn. Right, so then what do I get? I get curl of E equal to d mu tilde h over dt minus jm, where my jm is mu minus mu tilde dh over dt. Right? And similarly, I can say you can also derive rho m as minus of mu minus mu tilde times the curl of h, or divergence of h. Right? So in summary, I can say, okay, I can put this down. And I can write Jm as mu naught r tilde minus mu, sorry, mu r minus mu r tilde. Instead of using mu naught, let's just write it as mu minus mu tilde times dh over dt. Okay. All right, so here what we've done is we kind of generalize this idea. So we can replace mu with any other mu tilde as long as we place the right magnetic charges and magnetic currents to compensate for it. Okay, and a similar thing that we can do in place of epsilon is to replace epsilon with polarization currents and charges, which I'll say is epsilon minus epsilon tilde times dE minus dt or dt. And similarly, rho p equal to minus of epsilon minus epsilon tilde times the divergence of E. Okay. So here what we've done is we have taken epsilon and replaced it with epsilon tilde plus polarization currents now in charges. Okay, maybe it's a little bit easier to understand polarization currents because we discussed what the physical model is for epsilon when we discussed the Lorentz model, right? So we said we have these dipoles, small positive charge, and then we have this current for the electric negative charge distribution, which we can think of it as some kind of a negative charge with some center. And then this would then be our dipole, right? So when you have an incident electric field that's time varying, let's say it's some kind of a sinusoidal field, then this negative charge that we have here, right, it oscillates back and forth like that. Right? So as it's oscillating back and forth, that effect is captured by this epsilon, right? That's what epsilon is in some sense. So instead of dealing with epsilon, what we can say is that we can get rid of epsilon, get rid of the medium, and place equivalent currents that are oscillating back and forth. So it's a little charge that's moving back and forth is nothing but a tiny current, right? A small infinitesimal current. So you can place those infinitesimal currents instead of these atoms that are oscillating or these electrons that are oscillating, and that's what this means physically. Because it's not just a mathematical trick, there is some physical intuition behind it. Okay, so I want to make a few cautionary notes. So one is that these currents and charges and so on, I'm just mentioning currents, but okay, we can also mention charges, rho p and rho m, are dependent on the fields. Right, so they're not exactly sources in the sense of an impressed source, and we'll discuss what an impressed current source is at the end of the video today. But they are dependent on the field, so they're kind of a result of the fields, right? They're not provided as part of the source solution to the problem, as part of the source to the problem. They can be in certain cases, but it's important to keep in mind that they're coming from the fields itself, right? So that we'll discuss the nuance behind this at the end of today's video. But just keep that in mind. So there are some consequences of the fact that they come from the fields, and which means that Jp and Jm are in fact related. So they're not independent. Because of course E and H are not independent in a medium. They are related. So in the book, you can look at equations 2.36 and 2.37 to see where what that relationship is and where it comes from. Okay, I'm not going to do it here. It's not really that relevant. It's important to just remember that they are in fact related. Okay. So now that we've kind of developed equivalent charges and currents, then what we can do is we can revisit Maxwell's equations and establish something called duality relation. So this is the first tool that we will use in solving problems. So we're building up a toolkit essentially to solve Maxwell's equations. So one of the tools is called duality relations. Okay, so we can rewrite Maxwell's equations now. The minus mu dH over dt minus Jm. So I added the current. And here I'm using mu instead of mu tilde or mu naught. It's just a matter of convention. I guess you can think of it as the same medium mu and Jm is 0, or a different medium mu tilde with some value of Jm and so on. But just for simplicity, I'm calling it mu. It's just a matter of notation. Right? So then we have curl of H is epsilon dE dt plus J. And then we have divergence of H is rho m over mu. And the divergence of E is rho epsilon. Right? So now we see that there is some kind of duality or symmetry between these two and these two. Right? So that's what duality really means. Okay, so let's do that next. So what are the duality relationships? So duality relations. So what I can do, first I'll write it down and then we'll discuss what it is. So if I replace E with H, H with E, mu with epsilon, epsilon with mu, J with Jm, Jm with minus J, rho with rho m, and rho m with minus rho. Then, so I go back essentially, and in these Maxwell's equations, I make these substitutions. And you can convince yourself pretty easily that if you do that, you get back the same Maxwell's equations. So Faraday's law becomes Ampere's law becomes Faraday's law, and the Gauss will also get exchanged. Okay. So what does that actually give us? So that gives us the fact that if I have one set of solutions, which is these ones, Maxwell's equations in a given problem, I can just make these substitutions and for free get another set of solutions. Right? So that's what duality means. However, this relationship of duality is not very useful because I'm replacing epsilon with mu and mu with epsilon, which means that the solution that I get from applying duality is for a different problem where I've changed the material, right? So, and this kind of change is not really practical because mu and epsilon have about 4 orders of magnitude difference in their values, at least in free space, right? So they're usually very different numerical values. So having an epsilon with a numerical value of mu and mu with the numerical value of epsilon is not really realistic. So this simplistic kind of duality is not useful. Instead, what we use is called normalized duality, which is a different kind. There are other kinds of dualities as well. These are not the only ones, but this is probably the most useful, at least for us. So normalized duality relations, what are they? Right, so you replace E with square root of mu over epsilon h. You replace h with square root of epsilon over mu e. J with square root of epsilon over mu jm. Jm with square root of minus square root of mu over epsilon j. Rho with square root of epsilon over mu rho m. And rho m with minus square root of mu over epsilon rho. Okay, so when you do this, epsilon goes to epsilon, mu goes to mu, which means that the medium has not changed. And you can again do this. You can make these substitutions in Maxwell's equations, and you'll see that you get back the same equations, and epsilon and mu did not need to be changed. Okay, so that's very nice, right? So this exactly gives us what we want. We have one set of solutions, which is these ones, right? And then we make these duality relations, and we automatically get another set of solutions. And that's very useful, right? So we get it basically for free. We can actually take a quick example as to see how we can use something like this. That takes us to our next topic as well, which is we revisit the boundary conditions for these new set of Maxwell's equations. Okay, so we start with our boundary condition for H, which was Js, and this was derived from modified Ampere's law, right? And we haven't really changed Ampere's law by introducing magnetic currents and charges, so this remains the same. It doesn't really need to change. But now what I can do is I can apply duality to this. So when I apply duality here, I get nothing but n cross E1 minus E2 is equal to minus JSN. Right, so I didn't have to go back to the new Faraday's law and then rederive this boundary condition using the cylinders and all that. All you have to do is apply duality and you get automatically another boundary condition. Okay, so this is the boundary condition for electric field in the presence of magnetic currents that collapse into surface magnetic currents, right? So this is a magnetic surface current similar to an electric surface current. So similarly, we can do it for the normal component of D, which is rho s. In that place, I can apply duality to this, and I get nothing but B1 minus B2 equal to, is it rho or minus rho? Yeah, equal to rho m, rho Sm. Okay. All right. So given that we have magnetic currents and charges, we can also define a perfect magnetic conductor, PMC. So what is that? So I can say similar to how we had J equal to rho E, I can write Jm equal to rho mh, right? Where rho m is the magnetic conductivity. Magnetic conductivity, when it goes to infinity, that material is called a perfect magnetic conductor, PMC. Okay, and PMC has another special set of boundary conditions where the tangential H goes to 0, tangential E is equal to the surface magnetic current density, and similarly n hat dot P equal to rho Sm, and n hat dot P equal to 0. Okay, so you may say, okay, this is a usual question, is that I have perfect electric conductor, that's easy to visualize, it's just a metal, that's perfect, right? But do we have perfect magnetic conductors in reality? The answer to that is that you may not have it in reality because you don't really have real J and rho, Jm and rho m. But we'll see that we can actually engineer surfaces to look like perfect magnetic conductors. Or another application could be that these boundary conditions somehow turn out to be satisfied in certain problems. So I could have, like, let's say, a periodic structure that has unit cells like this. And for some reason or the other, we'll see maybe that at the boundary of each unit cell, these equations are, the fields satisfy these boundary conditions. So then what you can do is you can replace this entire periodic structure with just the perfect magnetic boundary condition and use a single unit cell. Right, so that we'll see can give us, so maybe, these boundaries are PMC boundaries. So that gives us a solution which is the same as having to solve this entire large periodic structure. So PMC boundaries actually are useful in many cases, and we'll see some examples of that later in the class. Okay, so that's about duality. It's a very useful tool. We've already seen one application of it already, but we'll see more applications. Okay, so the next thing we want to do is develop another tool called image theory. Okay, so before we do image theory, we need to take a quick aside and discuss something called uniqueness theorem, which we will prove rigorously and specify rigorously in the next lecture. Today, we'll just kind of talk about maybe what it is, because we need to use it in developing image theory. Okay, so what does uniqueness theorem say? So very roughly speaking, it says that if I have a closed surface bounding some volume, and if this volume doesn't have any sources, then if I know the fields on the surface of this volume, E and H, everywhere. So I don't need to know both everywhere. It says that you can either know E everywhere, or you need to know H everywhere, or you need to know E maybe in some region, and then maybe you have let's say green is H, and H in the rest of the region. Then the fields inside this boundary are unique and can be uniquely determined. Okay, that's what uniqueness says. It comes from uniqueness and differential equations, basically. And we'll develop it more rigorously in the next lecture. Okay, so what are the consequences of uniqueness, right? So one of the consequences is that, let's say I have some sources, J and JS, and I bound them in some volume. Okay. Now I can take another bigger volume outside. So let's use maybe gray. This is another volume outside. Okay. Draw that. Okay, so let's just deal with, since we need to know only one of them, we don't need to know both E and H. I'll just say that I know the E on the outer surface of the inner volume, which is this surface. Okay. And I know E on the inner surface of the outer boundary. Okay. So then if I consider this volume, which is this kind of spherical shell, I guess, or whatever, donut, whatever you want to call it. If I consider this volume, then for this volume, it has two boundaries, right? It has this boundary, which is the outer surface of the inner volume, and the inner surface of the outer volume, which is this boundary. Now, on this volume's boundary, I know E everywhere, which means that the fields in this region are unique, right? So that's what uniqueness is saying. For this volume, I know the fields on its surface, the boundary, which means that the fields there inside the volume are unique. Okay, then what I can do is I can send this outer shell to infinity in all directions, right? And then later we'll see that when you do this, the electric field and magnetic fields at the surface should go to zero. And that's called the radiation boundary condition, which we'll see later. And that's reasonable to expect that when I have sources in this region, which are finite in extent, the fields decay as you propagate further and further away, and at infinity, they go to zero. Right? So when I send that outer boundary to infinity, I know that the fields here would go to zero. I know this one would go to zero, which means it's determined. Right? So as that surface goes to infinity, I'm left with nothing but this problem. Right? So now I know this surface, the fields on the outer surface of this boundary, and it has some currents inside it. And from uniqueness, that fully uniquely determines the fields everywhere else in space, outside these source regions. Right? So that's what uniqueness is saying. Okay, so if you understand that, that's very nice because that's exactly what HFSS uses, right? You have an air box inside which you place your antenna and some port. We'll see this later. What HFSS does is it calculates the fields on this outer box. And then from that, it can calculate the far fields that you usually plot. And because the far fields are unique once you know what the fields on that surface are, on that air box are. That's the idea. Okay, so it's important to kind of see the distinction. In one case, we have no fields, we have no sources inside, and we have the boundary fields. In the other case, we have sources inside, so the fields outside the boundary are unique. And there are some technicalities with uniqueness we need to be careful about when we deal with resonance structures and cavities and things like that, which we'll cover in the next video. But for today, this is enough. Okay. Okay, so if you understand uniqueness, or at least you kind of get what we're talking about here, then we can go ahead and develop image theory. So let's do that next. Okay, so image theory says that if I have a PEC, this is a PEC surface, and I place some charge up here, some distance, then from uniqueness, we know that if I look at the upper half space, okay, if I know the fields on this boundary, or if the boundary fields are the same, if I maintain those, then the fields in this region are unique. Right? The fields, let's say, the fields are generated by this charge. I can get rid of the charge and have the same fields. I place some field distribution, which was originally created by this charge. And now it's a charge-free region. So if I just maintain the fields on this surface, then the fields in this region would be unique. Another way to say that is that if I have a fictitious boundary now, if I have a fictitious boundary where the PEC was, and I maintain the same boundary condition, the tangential boundary condition, so the tangential field is the same. I should also I don't know if I specified that, but I don't need just any field to be the same on the boundary. I only need the tangential component of the field to be the same. And we'll see that more in the next video, but that's what uniqueness says. So if I maintain the same tangential field, let's say the tangential E field, then the field in this upper half space is the same. Okay, so how can I do that? How can I maintain the same tangential field? I know since it's PEC that the tangential field at the surface should be 0. And I can do that by placing a negative charge on the bottom, symmetric to the positive charge. Then we can show from Coulomb's law, if I pick a point here, then positive charge produces a field like this, and the negative charge produces a field like this, right? Which means that the resulting field is something like this, right? And that has no tangential component, which means that the tangential E is the same for both these problems. And from uniqueness, they should have the same field distribution in the upper half space, right? So what we've done is we've replaced essentially the PEC. So we've replaced this PEC with this charge. Okay, and that's the idea. So how does that help us? So it really helps us when we deal with currents. So let's do that next. We take a PEC. Table it on the other side. This is my PEC. And I place a small current, electric current this way. And I want to look at what happens to that current. So what is that current, right? That's like charge plus Q, which is moving up, right? What happens to its image? Its image, of course, has to move down, right, to maintain that symmetry. And a negative charge moving down is the same thing as a current moving up, right? So if I have a current like this, then its image has to be like this, right? So the right way to think about this maybe is to say that I have a very long current filament that I look at a small section of it, and it looks like its image is also moving in the same direction because it's a negative charge going in the opposite direction. Okay. And now if I take the same charge and I move it to the right, and of course its image also has to move to the right, which means that the current has to go to the left. I have this current there, which means I have a current that goes like this. Okay, so that's how it helps, is that if you have PEC with some current distribution above it, you can replace that PEC with an image current below it. Right? And of course, keep in mind that this only gives us the right field in the top half space. In the problem on the right and the bottom also there are some fields, but there should not be any fields here because this is PEC. Right? So image theory is only valid for the upper half space. So these two are equivalent for upper half space. Let's see. Upper half space. Okay. So now what I can do is I can apply duality to this problem. And that gives me another set of solutions. So dual of PEC is EMC, and dual of magnetic electric currents are magnetic currents, right? So I can erase this, paste that there, and we can make magnetic currents with two arrows. Then the dual case is nothing but this. Right? And one thing to keep in mind is that if I have some arbitrary current distribution in some direction, And I can, since it's a vector, I can break it up into its two components and then take the images of the components and then add them back up, right? So that treats all cases essentially. Okay, so we've dealt with electric currents over PEC, magnetic currents over PMC, but we still have two more cases, which is electric currents over PMC and magnetic currents over PEC. Right, so let's do that. So we'll do first electric currents over PMC. So I have electric current like that, maybe like this. And the boundary condition that we want to maintain is that the tangential H has to go to 0 everywhere. So I said we can do either E or H for uniqueness. So here we'll do H. Okay, so if you want the tangential H field to go to 0, then the question is, since it's PMC, what should be the direction of the magnetic field? The electric current in the image. So image has to look something like this. And to determine that, we can use the right hand rule, right? If I have an electric current going up like that, then the magnetic field at the boundary should be counterclockwise looking from above. So I'm looking down from above, and the right hand rule should be counterclockwise, right? And for the right hand, so to make my image and cancel that counterclockwise current, I need a clockwise current, which means that the current should be flowing down, right? So that gives me my clockwise current, and then they both cancel. So that's fairly easy to establish. Now in this case, since I have a current going in the right towards the right, my magnetic field from right hand rule is going into the page. So I need on the bottom current to go to the left so that the no, it has to still go to the right so that the magnetic field is coming out of the page. And you have to use the right hand rule to do that, but it's fairly easy to see. Okay, which means that this one has to also go to the right. It makes sense. It has to be the opposite case of PEC, can't be the same thing. So that's what we get. And then once again, we can apply duality to this to get PEC with magnetic currents on top. Okay, so that gives us, it's like this. And the image is in the other direction, vertical case, and same direction for the horizontal case. Okay, so these are very useful and we'll see an application of them shortly, but maybe let's summarize them in one place. Okay, so in summary, let's take each case separately. We have our PC case. PC with electric current and magnetic currents. And then on the right, we have our fictitious boundary. And the images which we discussed earlier look like this. Right? And then we can also do the PMC case. the images are flipped. Sorry, this should be right. PMC with magnetic fields. If we go back and check, PMC magnetic fields are in the opposite direction. Uh, That means here they should be in the same direction. Right, magnetic fields with PEC should be in the same direction. Yeah. Okay. And then this one should be going up. Okay. So that's the summary. So it's important to keep in mind that these are only valid for planar infinite boundaries. Infinite boundaries. So if you have curvature in the boundary, you can't use image theory, at least the way we developed it here. There are ways to deal with that. But the way we developed it here is only valid for planar boundaries. And they're really valid for impressed currents. So we'll discuss what this impressed current versus induced current is at the end of today's video, right? So it's actually a nice way to look at why, for example, if I have a ground plane, which is nothing but a PEC, and I place a current on top of it, electric current, it cannot radiate because its image is in the opposite direction and they cancel each other out, right? And that's the reason that a dipole over a large ground plane, if you place the dipole very close to the ground plane, it doesn't really radiate. It's very hard to get that to radiate. Similarly, for a patch, if it's very close to the ground plane and there's not enough spacing, then we'll see that the bandwidth would be very limited and it's very hard to match to that patch. Okay. All right. So we'll take a quick example and show how image theory could be used. So let's say, you're asked to solve this problem. This is one of the example problems in the book as well. So you're in the XY plane. You have a loop of current, circular symmetric loop of current about the XY plane. And it's carrying some current I. And you're asked to prove that the electric field generated by this current has no Z component. So of course you can go ahead and calculate the entire electric field in space because of this current and show that it has Ez equal to 0. But a quick way to do it would be to use image theory. So how would you do that? Right, so you go back, you draw this XY, and I take just a half circle and I would place a PEC here in the XZ plane, and I have my current like this. Now what you can do is you can say, okay, are these two problems equivalent? And you can show that they are equivalent because this place the current is going up, and which means that its image is also going up. Here the current is going down, so the image is going down. Out here the current is going to the left, which means that the image is going to the right. And you can show for every section in the top, the bottom has an image which corresponds to completing the loop. Okay, so essentially these two problems are exactly the same because the current on top is a full circle, whereas the current on the bottom, because of the PEC, you have an image of the top circle, and that is exactly like completing the full circle. So you get back the same loop. Okay, so since these two problems are identical, the electric field in the bottom problem on this tangent, the tangential electric field, we know is 0 because this is PEC, right? So in the XZ plane, E tangential is 0. Now, the cool trick, I guess, is to say that, okay, I place the PEC in the XZ plane, but I can place the PEC in any plane. Suppose I place PEC like this. And it's still the same thing because you have half semicircle here, and its image forms the rest of the circle, right? Now, of course, also in this tangential plane, in this plane also the E tangential has to be 0. And that's true for any plane. Right? So I can take any plane and rotate it about. So I can take, this plane, this plane, this plane, this plane, all of them will give me the same problem, right? And in all of them, the E tangential is 0. That can only be true if EZ is equal to 0, right? It's in fact true also that E rho also must be 0, right? Because E rho is in this direction everywhere, right? And for a given plane, that would be 0. So this is another way to say that E has to only have, these should not be vectors. So E can only have an E phi component, E phi hat. Okay, and that's a nice proof using image theory. Okay. So the last topic for today is to discuss the difference between induced currents and impressed currents. This is usually a confusing thing, a confusing topic, if you're looking at it for the first time. So I think it's important to spend some time and kind of clarify what it is. Right, so broadly speaking, you can kind of classify currents into two parts, two categories. They can classify them as either, let's call it impressed currents. Let's charge my iPad. So impressed currents or induced currents. Okay, so what's the difference? So impressed currents are source currents used in Maxwell's equations to solve for the fields in a given problem. So what do we mean by problem? In a given, in a given medium or given boundary condition or a given distribution of materials and so on and so forth, right? So you're given some waveguide problem, antenna problem, scattering problem, and there is some source in that problem, and that source is specified, and then you're asked to find the fields. So those are the impressed sources or the impressed currents. Induced currents are currents generated by the fields that are solved for in a given problem. Okay. So you're given certain impressed currents, you solve for the fields, and then the fields with certain material properties will give you these induced currents. Because this classification is not exactly either or, and we'll see. For a given problem, you can separate currents into impressed and induced. But for a different problem, induced currents could become impressed currents, and we'll see when we take examples next. Okay, so good example of this would be a lumped port in HFSS or wave ports and so on. These are all sources. Okay, and examples of these are, so, 'okay, examples of these are, 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 'okay, ex conduction current, a good example, right? Which is J equal to sigma E. And then you can also say you have polarization, magnetization currents, right? Where you replace epsilon and mu with Jp and Jm. Or you could have surface currents that are established to satisfy the boundary conditions, right? J equal to n hat cross h1 minus h2 and Jm equal to n hat or minus n hat cross E1 minus E2. Right, so given certain incident fields, we can say that you have equivalent polarization currents, or you have conduction current, or you have some surface currents that are used, that are placed to that are induced to satisfy boundary conditions, right, or the given fields. Now, the subtlety comes in as to how you exactly define induced and impressed currents, right? So let's take an example to see that sometimes actually induced currents can become impressed when you change the problem definition. I mean, impressed currents like these lump ports, wave ports, they have to come from somewhere, and they don't come uh, from nothing. So since they come from something, they are in fact induced by some other source that is outside the problem statement. Okay. So for example, let's take a simple example and see the difference as to how an induced source can become an impressed source, right? So let's say I have some current distribution. This is my impressed current, which is given to me. And I have a PEC, ground plane, some kind of plane, metal plane. And we want to solve this problem essentially, okay? So you'll see that once you solve the problem, there will be some current distribution on this surface, J, S, which is given by n hat cross E, n hat cross H, right, to satisfy that boundary condition. But when we solve this problem, we already solved for H everywhere when we solve the fields everywhere. So we know HJS is nothing but n hat cross H total. Right, so then again, we don't have to solve for the fields radiated by this J, because that is already solved for when we solve for the fields E and H. Okay? So it would be like double counting if you do it again. But another way to solve this, let's say this was solved using finite element, right? You put this into HFSS and then solve for the fields everywhere. It's a 3D problem. And then from that, you know what the H total is on the surface. And from that, you can say what the currents are. Another way to solve this problem would be to say that I have this source, I have my PEC, but instead of placing the PEC there, what I can do is I can find this JS as some function of the H incident. So you have some incident field, right? This as if it was free space. So then you find what that incident field is on the surface, and we will show that for certain simple geometries at least, or some simplified geometries, you can approximate this current distribution on the surface of this PEC. Let's actually say this was PEC as a function of just the incident field. Right? So incident field is way easier to solve because you only have to solve the free space propagation from this current distribution that was given. Right? And we'll see we can do that using something called a Green's function. Right? So you know what the incident field is. From that, you can approximate what the surface current distribution is. Now then what you can do is you can say, okay, given that surface distribution, now I can find the field everywhere. Do I that again? Okay. So given this current now, Js, which is just a function of the incident field, I can find the field everywhere. right? And in this problem, both J and JS are impressed. So this is impressed. This is also impressed, or a source. And you don't have any PEC now. You only have free space, right? And you can actually, it's kind of cool. You can show that if I have both the original source and this new impressed source, and I find the total contribution of both of them, then the E and H inside this region would be 0. Because originally you had a PEC, right? So if these two problems have to be the same, the total field, which is the original impressed field from this one, original field, which is the incident field from this one, and then the field scattered by this PEC, they would add up in such a way that the field inside the PEC would go to 0, or inside this region would go to 0. This is called the extinction theorem, which we will maybe look at later. Okay, so this is roughly speaking called the integral equation or method of moments way of solving it, right? Which we'll see later on how to do it. So in method of moments, you only find the sources, the currents everywhere from the incident current, from the original current. And once you have all the currents, then you treat all of them as sources, and then you find the fields in free space, right? Whereas in the FEM, you find the fields directly from the original sources. So both problems are solving for the same fields. In one problem, we treat only the original sources as impressed and the rest of them as induced. Whereas in this other problem, we have impressed sources as from the original source and also impressed sources from the induced source, from the induced currents, right? So it's kind of important to understand that given a certain problem, it's important to know which sources are impressed, which sources are induced, in terms of current sources at least. And you can make the same classification for charge distributions as well, but we usually just deal with the currents because in metals at least they are charge neutral, so you don't have any net charge, right? So for most scattering problems, antenna problems, things like waveguides, we usually just deal with currents. Okay, so hopefully that's at least a little bit clearer as to what's the difference between all these current sources and how they can act in a given problem. And as we do many examples in the future, we'll see what the difference really is between these two cases and when to treat something as an impressed current, when to treat something as an induced current, and so on. Okay. All right, with that, we will stop. So just to quickly review, we started with developing magnetic currents and charges, and we said we can replace materials with these charges and it would behave the same way. We can do the same thing for polarization currents and charges. And then we developed duality relations from making Maxwell's equations symmetric. And we said that given a set of solutions, you can find another valid set of solutions just by applying duality. We use duality to develop boundary conditions for magnetic currents and charge distributions. And we defined what is a perfect magnetic conductor, PMC. Then we briefly introduced uniqueness without proving anything or stating it rigorously. And then we used it to develop image theory, which is another useful tool when you have planar PEC and PMC boundaries to get rid of them and place equivalent current distributions so that you can solve a free space problem. And we really like to do that as much as we can, is just to deal with free space propagation because we have an analytical solution for free space propagation, which we'll develop later. And then we kind of summarize those results, and at the end we looked at a simple example on how to use image theory, and we also categorized currents into impressed and induced currents for a given EM problem. Okay, so with that, we'll stop here. And in the next lecture, we will develop some more tools and theorems. Specifically, we'll develop Poynting theorem, which is how energy propagates in electromagnetic waves. And then we'll use Poynting theorem to prove uniqueness theorem, which is actually very powerful, and we'll see why it's so powerful. And then we'll use uniqueness to develop one more very useful tool called the field equivalence principle. So that's what we'll do in the next lecture. So hopefully you're excited about that. If you have any questions, leave them in the comments below. If not, I'll see you in the next one. Thank you.